Hello, everyone. I'm really pleased to welcome you all to this first GEO-Wednesday for this semester. And we are so lucky that we have our professor, Clint Conrad, professor in geodynamics, will talk to us about the changing sea level. Clint came to us in 2016, and he speaks fluently Norwegian, but he will do this talk in English just to avoid some problems and misunderstandings and things. So I think since we're a bit late, I think we just start there.
There you go. Now you're on.
Okay, yeah. It's certainly a pleasure to be here today to talk to you about one of my favorite topics, which is sea level. And I hope you all have been enjoying this photo of sea level for the past few minutes. I like this photo because it doesn't really have much human activity in it. So you can imagine that we could have taken this photo millions of years ago, and the ocean would be large like it is there, and sea level, presumably, there certainly was a sea level at these past times, and presumably it's been changing with time, and that's what I'd like to talk to you about today, how sea level has evolved with time and how it was different in the past. Okay, so as humans, we are mostly interested in sea level because at the place where it interacts with land. So that's what controls where we live. For example, these are 3 other pictures of sea level that I've taken at different parts of my life. I used to live in Hawaii, and this is a map. This is a picture of the city of Honolulu. You can see the buildings and everything go right up to the edge of the sea level. Here's Oslo. This is the castle near the harbor, and we often, as humans, build important things near sea level because of military and commerce and recreational activities. And this final one is up in Denmark, and this is kind of a more natural interaction between the sea and the ocean, and the land. So sand dunes form naturally at the boundary between at sea level, basically. Okay, so what I'd like to talk to you about today is if sea level changes with time, then all of these things will be affected. And here's an example, a recent example of you see sea level in the news all the time. This is one recent example. Florida Keys deliver a hard message: as seas rise, some places can't be saved. So sea level rise has been in the news. This is a place in Florida where they've determined that it's just too expensive to fortify the road to this community, and so they have to make a choice. Are they going to save the community and fortify the road to raise it up above future sea level, or are they going to ask people to move? And these are some of the choices that people have to make, or increasingly are starting to make. You can see that this is one indication of sea level rise, is all these trees near the edge are dead because of saltwater inundation. Okay. So this is a place where we think sea level is rising and will rise in the future. Sea level has been different in different places. This is an example of a place, which isn't too far from here, where sea level has been dropping. This is the Celsius stone, named after, or not named after, but named by the famous Celsius of the temperature scale. And this is off the eastern coast of Sweden. And Celsius noted the height of this stone above sea level in 1731. And then it's been recorded since, and the stone is rising up out of the water. So this is a place where sea level, relative to the land surface, is dropping. Here's another place, back to Hawaii, where sea level has dropped. This is this island. There's a little island off the coast. You can see this little island right there. It's called Flat Island, obviously, for obvious reasons, and it's an old coral reef. It's a coral reef from 120,000 years ago, and we all know that coral grows underwater, so this was formed at a time when sea level was higher than it is today. And here's a reconstruction of what we think sea level did in the past several 100,000 years. It's been going up and down. It was formed at this time, which was the last interglacial time, the time between big ice ages. We're in an interglacial period now, so we have relatively high sea level, and it was even a little bit higher at that time, it's thought at least. And so then the ice ages came, used a lot of water from the oceans, put it on land in the ice sheets, and then that all melted, and we'll talk about this in a little bit later, and moved, and sea level rose back up to the present day. Okay, and here's a final example of sea level change over a very long geologic time. This is a map of the world about 100 million years ago, and you can see the reconstruction suggests that the ocean was inundating many of the continents. And one explanation for this is that sea level was just much higher then than it is now. This is the time when the dinosaurs were roaming the earth and things like that. Okay, so I've shown you 3 examples of sea level being higher than it is today. Oh, and yeah, here's a reconstruction of sea level through geologic time, 500 million years. Pangea assembles, is present, and then disperses. And then finally, and during this Pangea time, we had relatively low sea level. In between, as it's dispersing, sea level rose and then fell down to the present day. Okay, so what I'd like to do, I'm a geodynamicist, so I always like to think about the causes of of something like a sea level change. And so what are the processes that cause this sea level rise and fall through the geologic ages? Okay, so one way you can do is think about the oceans as the ocean basis as a container, and the container is holding water. So how can we change that level of the top level of the water? Okay. I asked this when I was in Hawaii. I did some outreach stuff, and we did a unit on sea level with 3rd graders, I think they were. And they did an experiment where they took a plastic cup with water in it, and I have an example of that here. And we say, well, what can we do to change the level of the water in the cup? Okay? And so if you ask 3rd graders this, they have all kinds of ideas. There's the obvious one is to add water. So you can add ice to the water, and that's what we did. So you put ice in, and the level rises from there to there. So that is an obvious way to raise the level of the water. If you ask the 2nd graders, what happens when the ice melts? Does the level change? I don't know. What do people here think? Would it go up? Say the same. Okay, sometime between now, your age, and when you were in 2nd grade, you learned that because most of the 2nd graders say that the water will continue to go up. And so we do an experiment, see that it doesn't actually go up. But if you heat the water, if you heat it enough, the water level will go up because of thermal expansion of the water. So that's the second mechanism that you can raise sea level, is to actually heat up the water. Okay, so you can do things to the water, and you can also poke a hole in the bottom and leak the water out the bottom. You can do things to the cup. So for example, if I squeeze the cup, the water level goes up. If I were to push on the bottom of the cup, it would go up. If I put things in the cup, coins or something, it would also raise the level, displace the water. So you can do things to the container, which would be the ocean basins, and that changes the water level. And then there's another thing you can do. You can change the water level in one place and not the other by tilting the cup. So you raise it here and lower it here. You can also do something, and if you had a big mass right here, it would pull the water towards the mass. And so that would change. It would be like the opposite of tilting the cup. You're changing gravity. So that's another way. So those are 8 ways that that you could change the level of the cup, the level of water in the cup. And the Earth does all 8 of these in order to change the level. It just happens on different time scales. So the slow leak from the bottom of the cup, that is a process which I'll talk about next, but that happens over billions of years, or we think it is. And then things, heating the water, changing gravity, those are things that are happening on an annual basis and on time scales much shorter. So all of these processes are happening, and I put them in a kind of a relative order of how fast they happen. Okay, so let's talk. I'm going to go through all 8 of them and talk about how they are important for the Earth at different time scales. Okay, so we'll start with the slow leak. The mantle, the interior of the Earth, is thought to hold several oceans worth of water. And this water is stored as hydrated within the hydrated structures of minerals in mostly the upper mantle. It gets into the mantle because some of those hydrated minerals are found in the water, in the rocks near the surface, and they get subducted into the interior, and the water is incorporated. Some of it comes straight out of a volcano, but some of it gets incorporated into the rock structures and is held in the interior of the Earth for a long time. And then it's replaced to some extent by water coming out of the volcanoes, like at mid-ocean ridges. Now, if these two the rates of these two fluxes are imbalanced, then you could get a net accumulation of water in the interior or the opposite of that. So are they balanced? Now, one thing that you can study this by looking at how much water rocks can hold as a function of their temperature and pressure and things like that. And combine that with what temperature we think the rocks are as they go down and so forth. But one thing, if you do all those experiments, one thing you find is that colder rocks tend to hold more water. Okay, so this is the subduction zone going down. You can think that the hottest part of the subduction zone would be on the edges where the hot mantle is. And most of the water, which is shown in the lighter colors there, is held in the middle of the of the slab that's going down. So most of the water would be held in colder rocks. So therefore you could say, well, as the Earth cools down, then it should be able to hold more water, and the stuff going down would be colder, so it should be able to carry more water. So you could say that as the Earth cools, it should be accumulating water in its interior, and that gets that water from the surface ocean. So Christer Carlson, who's a PhD student here, maybe he's here. Yeah, he's here. And he wrote a paper last year which estimated what the imbalance was over the past 200 million years. And he came up with several different models of estimates of how much water is being lost to the interior of the ocean, interior of the Earth. And it's up to about 100 meters during the last 200 million years. So some of that sea level drop that I showed you previously, that could be due to water loss from the surface of the ocean into the interior. And certainly over geologic time, since the beginning of the Earth, we think that the oceans have been slowly draining into the interior of the Earth. Okay, so that's the slow leak. I'm going to talk now about deforming the base of the seafloor. The seafloor has topography on it. In fact, the most prominent thing are the ridges. These are ridges that cover, and I'll show you a map of it in a sec, but the mid-ocean ridges, if they are spreading fast, if plate tectonics is moving fast, then the ridge is wide. If it's slow, then it's narrow. And so a wide ridge, fast spreading, would take up more space in the bottom of the ocean, and then you'd expect sea level to be higher. So Christer also made a movie of plate tectonics, and this is estimate of where the plates were in the past and how old they were as a function of time. And then you can convert that to height of the ridge. And so this is bathymetry. So the blue colors are very deep, and the lighter colors are shallow, so you can see the ridges. here, it'll play again. But then you can calculate the ocean basin volume and see how it affects sea level. And so the blue colors here are sea level estimates from sedimentary rocks. These are basically observations of sea level. And the red is the calculation that Krister did with an estimate of how much the volume of the ocean basins has changed and how that would affect sea level. So during this period, the oceans were on average very deep. You had very few ridges, and now you're accumulating more ridges on the bottom of the ocean, and you get it displaces seawater and brings it up. So you see that cycle of high sea level before and after Pangea and low sea level during Pangea. That's mostly due to changes in the ridge structures in on the bottom of the seafloor. Okay. Another thing you can do is put objects in the cup and displace the seawater. So this is a picture of the bathymetry around the island chain of Hawaii. There's the big island. That's where Honolulu is. And I did a small calculation. The presence of just this one island in the ocean, the fact that it's there, raises sea level everywhere by about 3 centimeters. So if you have have a geologic period of time when there's a lot of islands, then you would have, or a lot of volcanic islands, then you'd have higher sea level. Another thing you can see here, and I always found this to be kind of amazing, is this big debris flow off the coast, off the north shore of Oahu and Molokai. These are big slumps where the side of the island just slumped into the ocean. It's a sedimentary process, and presumably that also displaced seawater and raised sea level. So the sediments in the ocean, all the little volcanoes in the ocean, those all make sea level a bit higher and displace seawater. So we can estimate the volume of all those things, and then the harder thing is to estimate how they've changed with time. But, okay, the map here in the background colors is the sediment thickness. And it varies between very thin, the yellow colors, to very thick. And very thick is typically on the edges of the continents because that's where a lot of the sediment's coming into the ocean. So you have very thick sediments. The average of all this is somewhere around, actually I can't remember, I think it's about 200. But so the sea level is offset by that much because of all the sediments in the ocean. If that changes with time, and we think that at a time when all the seafloor was much older, then it should have, which would cause the seafloor to be, the ocean level to be deeper, then it should have more time to accumulate sediment, so you should have higher sea level due to the sediment. So that kind of offsets the ridge calculation. All the little dots are, and the sediments, we think that since the oceans have been getting older, then they've had more time to accumulate sediments, and so that should cause sea level rise in the last, say, 70 million years. The volcanics are even a little harder to estimate, but each one of these dots is a little seamount. That's a little volcano under the sea level, and if you add them all up, they raise sea level by about 20 meters. And if you include there's some big ocean, big plateaus that were huge volcanic events, and if you include those and estimate how they've been changing with time, I estimated that it's a slow drop from volcanics for recent times. Okay, so you can add stuff to the oceans. You can also deform the sides. I showed you that example. Basically, what you're doing, if you deform the sides, you're changing the area of the oceans. And so for example, if you have India crashing into Asia, it causes the uplift of Tibet. But basically, that shortening of the continental crust is compensated by an increase in ocean area. So if you increase ocean area and keep everything else the same, then the sea level should go down. And that, we estimate, caused a sea level drop of about 25 meters in the last 50 million years. Okay, so I've talked about 4 different processes happening over geologic time, and Krister put them all together into one curve. And the biggest one is the ridge volume, and then you have the sediments going opposite to that. If you put them all together, then you have the ocean. If you're just talking about the changes to the ocean base and volume, then you get this curve. If you add that slow leak of water into the interior of the Earth, you get the solid red curve. And so together, they approximately show the same trends as the observations. Okay. I want to move towards more recent times. And what I'm showing you here is that ice age. I already said that this sea level curve for the past several 100,000 years is associated with the growth and the shrinkage of the ice sheets. Here's a map of the ice sheets that were shrinking around this location, or actually around here. 23,000 years ago that's about at this little minimum here, is the maximum of the ice age, the last ice age. And since then, the ice sheets have been slowly shrinking. And so all of Scandinavia, the British Isles, were all covered in ice. That ice has melted, and at 4,500 years ago, it would look approximately like this. So it was gone mostly from British Isles, but still a lot in Scandinavia. This time here, 4,500 years ago, that was the time of the fastest melt. And the rate of rise at this time was about 50 millimeters a year. So that's 5 centimeters a year, about that much. And that was the fastest melt during the last ice age. That's how fast it can get. And we can compare that number to estimates that I'll show you later about how fast we think it's going to melt in the future. Okay, just to show you a picture of what that melt looks like from an ice sheet. We were flying, I'm part of this MAGPIE project, which is NFR funding, and our ultimate goal of this project is to constrain the melting rates on the Greenland ice sheet, which we think is an important source of melting today. So we were working high up on the ice sheet, in the middle of the ice sheet, last summer, and when we flew there, this is on the west coast of Greenland, and we're flying into the interior, but as you go through, you see all these little lakes. That's meltwater on the edge of the ice sheet. That is the ice sheet melting in real time. Eventually, this melt finds its way, either runs off the top or finds cracks and stuff and goes down below and gets into the ocean, most of it, or some of it. What happens to an ice sheet after it melts? What happens to the rocks after it melts? And this is going to become important because now we're starting to talk about geologic processes that will cause the tilting of the seashore, which affects sea level regionally. If you take an ice sheet and you melt it, then you've removed a lot of mass from the surface. That the Earth responds by trying to fill that void of mass. And so basically you have viscous flow to move into the space left by the ice sheet. So places next to the ice sheet go down, and places where the ice sheet used to be go up. That's a tilting process, and it affects sea level. This is what that process looks like right now in Scandinavia. You can see all of these colors are positive rates of uplift of the surface, and it's largest where that ice sheet used to be. So where it used to be, it's almost 10 millimeters per year. This is the location of that Celsius stone that I showed you earlier, and that's why that stone is rising up out of the water over the last 200 years. This process and these rates have been going on for thousands of years, and they're continuing. This is something, we're kind of lucky here in Scandinavia because most of Scandinavia is rising up because of the past ice being there. As a result, when sea level rises everywhere in the world, we experience it a little bit less because our land surface is rising. So the sea is rising and the land is rising, and we rise together. Okay, If we look all over the globe, we take kind of averages of the sea level rise from locations all around the world, and we have some measurements going back even 100 years from tide gauges at many ports. Then you get a curve like the red one. And the red one was part of a project I was involved in to try to, what we did is instead of just taking the measurement of the sea level rise at those ports, you take an estimate, you also include an estimate of how much the land surface is going up and down. If you do that, then you move from sort of the purple curve onto the red curve. And the red curve has actually slower sea level rise at these early times in the past century. But as you move towards the present day, all the curves are the same. And it's about a little bit more than 3 millimeters per year. But early on, it was maybe, before 1990, it was maybe only 1 millimeter per year. And so this means that sea level rise is accelerating and has accelerated in the past 100 years, or past several decades. You have a factor of 3 increase before 1990 and after 1990. Okay, and then this yellow curve, since about 1992 or 3, we have satellites that actually measure the sea surface everywhere, the elevation of the sea surface everywhere, and you can get satellite measurements. So those are thought to be pretty good estimates, and it's comforting that all of them show the same trend. This is what those satellite measurements tell us for the period 1993 to 2018. And you can see that it's all red. So here's rate of sea level rise. Everything's in this 3 millimeters per year, but there are some variations. Some places are rising faster than others. That's an interesting observation, and it's a good question of why that is. If I subtract out the average rate of 3.1 millimeters per year, then this is the curve you get. And now some places are going kind of slower than the average, and some places are going faster than the average. Now, to understand these patterns, and I don't think they're fully understood actually, we need to know what the processes are that's causing this 3 millimeters per year. So to find that out, we can go. There's actually the International Panel on Climate Change, Intergovernmental Panel on Climate Change, made a special report 2019, and there's a whole chapter on sea level rise. This is one of the figures from the executive summary for policymakers, and it shows sea level. These are observations of sea level up from in the 1900s up to now, and then this is all projection into the future. This is a scenario of we keep going with the same greenhouse emissions that we do now, and this is if we do something about it, basically. And the worst case is that we get up to about 1 meter of sea level rise by 2100. That's kind of the estimate of what people think. So what are the most important sources? And this report gives an estimate of that and some projections into the future, so we can look at that and see what the most important sources are. So I've divided them into 2 groups. The first is thermal expansion of the seawater. The seawater gets hotter because of climate change, and it takes up more space in the ocean, and the ocean rises. And so this has caused about 1.4 millimeters of sea level rise since 1990 in this period. And then we can melt ice and put new water into the oceans, and you have some from Greenland, Antarctica, the glaciers, the mountain glaciers. If you add them up, that's about 1.3. So this process is biggest in recent times. But, this thermal expansion of the seawater. But this one is catching up. You can see that some of these, like Antarctica, was basically 0 until recently, and it's accelerating. So these melting processes are causing more and more sea level change. Okay, so if a lot of the sea level rise in this satellite observation period is caused by thermal expansion of the seawater, then you would expect that a lot of these variations would be could be associated with that. So these might be, and it's thought that they're partly reflecting variations in the heat content of the oceans. So these parts of the oceans have gotten hotter and the water is higher. There's other things that go into this. long-term changes, partly as a result of climate change of the ocean currents, or steady changes in the wind patterns that kind of push the water around. Those things are also thought to be important and contributing to this to these patterns. It's important to know how it's important to try to predict what these patterns will be like in the future. Because you can see, remember the average was about 3, and some places here in the Western Pacific have another 3 on top of that 3 that I already removed. So these places have been experiencing sea level rise of 6 millimeters per year. Whereas other places, say west coast of the US, some places in the North Atlantic, they're experiencing less sea level rise than the average. So it's important to try to understand if these patterns will continue into the future or if new patterns will emerge. So to do that, let's go back to that curve that I showed you before with the 4 different ones and just look and let's see what the worst case scenario is for 2100. And I've measured the slope with that line, kind of estimated it. Thermal expansion, 4.5 millimeters per year. So that's about triple what it is now. These other cases are much higher than they are now. So these cases where you're melting ice and put it in the oceans, those are accelerating faster than this thermal expansion is. So this predicts that in 2100 we'd have double the rate of sea level rise caused by melting of ice compared to thermal expansion. That's the prediction at least. So it would be good to know if you melt this ice, what sort of patterns of sea level rise should you expect? Does it all go evenly, or do you expect things to change? And that's where this change gravity, the last mechanism that I wanted to talk about, comes in. Okay, so if you have, this is in real time, if you have an ice sheet and it melts, then the mass of that ice sheet becomes smaller, and so the ocean water is not as attracted to the mass of the ice sheet anymore. And this is a real effect that as you melt the ice, the sea surface falls away from the ice. The land surface also goes up because there's an instantaneous response of the rocks to the loss of ice at the surface. And so you unload the surface, the land goes up, the sea surface sinks, and you actually get sea level drop near the source of the melting. So it rises everywhere, but near the source of the melting, it actually drops. And here's a map of, I found a paper that had an estimate of all the melting that happened on the Earth in 2012. And some of it's Greenland, some of it's Antarctica, and some of it's mountain glaciers in various parts of the world. And I calculated the change of the gravity and the uplift of the surface. And so this is showing what the sea level would be like in various different parts of the world. This interface between blue and yellow is 1.5 millimeters per year. That's the average of all that melting. And so it would be right about here. Those right at that interface is kind of the average. Everything that's pink or peach or red is rising faster than the average. So that is places that are far away from the ice sheets, or far away from the sources of melting, like Hawaii, for example, would experience sea level rise greater than the average. And places close to the ice sheets that are melting would experience sea level rise that's less than the average. That includes Greenland, and Norway is actually close enough to Greenland that we're experiencing, it's still sea level rise due to Greenland, but it's not nearly as much sea level rise as a place that's far away from the ice sheets. So again, Scandinavia is a little bit fortunate compared to other places because we're near a source of melting. But if Antarctica starts melting really fast, we're far away from Antarctica. So that would cause more sea level rise in the far northern hemisphere. Okay. This is taking all these things into account. There's a really good report, sea level change for Norway. and projections to 2100. I think this, for example, this hasn't been updated for the most recent IPCC report of 2019, but the estimates are pretty good. And so for Oslo, which is here, the past 100 years had a sea level drop, and then projecting it, and now it's starting to slow down because of sea level rise. And then projecting into the future, it could even, in a worst case scenario, sea level would go up in Oslo. Bergen is, instead of on these yellow colors, which is 6 millimeters per year, it's on the green, which is only 3. And so Bergen is farther away from the ice melted in the deglaciation times. And so it doesn't have the sea level drop. It's more of sea level steady. And so when you add on the rise in the future, Bergen should experience sea level rise more than Oslo will. Okay, so sea level rise is coming even to Norway. Oops. Okay, so I want to talk about what happens to a coastline when sea level rises, because this is what's really important, at least for human society, is how does the shoreline respond? How do we respond as humans to that change in the sea level? And if you're in a beach area, so some of this is inspired by my time living in Hawaii, where there's a lot of beaches, but we have similar beaches. There are beaches in Denmark too, and parts of Norway too. You have, if it's a sandy area and the sea level goes up, then basically you remove sand from the sand dunes and deposit it here, and the sand dunes move back. They move away from, they just retreat as the ocean level goes up. And they retreat kind of when everything has a chance to adjust. The rate of retreat depends on the rate of sea level rise and the slope. And so in a lot of places, kind of an average slope is 100 to 1. And so if you have 3.5 millimeters per year of sea level rise, that would be 35 centimeters per year. That would be over 10 years. That would be 3 meters, so kind of the distance like this. That's kind of over a decade. And so if that keeps up, you start losing land. I'm going to show you a picture of a place where this actually happened, and some of this is due to subsidence of the land, which accelerates the sea level. But this is Holland Island in Maryland on the east coast of the U.S. The slopes there are not 100 to 1; they're more like 1,000 to 1 or 5,000 to 1, and so it's very, very flat. So any kind of sea level rise or subsidence of the land is experienced quite strongly. And this is a picture. This is a community of 350 people on this island, living on this island in 1910. Sometime in the 50s, they had to abandon the island. And this is in 2003. You can see that house is still there. 2009, totally abandoned, and now it finally wrecked in 2011 around then. So this is, if left to its own devices, this is what would happen to a community that is on a very flat place, and if something isn't done to protect it. So what can you do to protect it? Okay. Oh, and here's another example that's happened recently in Hawaii. On the North Shore, where the big ocean waves are, that the surfing competitions and things like that are, there's a lot of coastal erosion. So this is the ocean trying to move the shoreline back due to sea level rise. And so these houses are in the way of that. And so it's a big problem. What do you do in a situation like this? These are multi-million-dollar houses. And how should the community respond to that? Should we ask these people to move and suffer the financial loss? Or does the community support that? It's an ongoing question. But one solution is to build a wall of some sort. And this is what happens if you build a wall. They're doing this in Waikiki, in places where you build a wall, and the ocean will just erode that sand back, and then you have the ocean right up to the wall. And that's what's happening here. Coastal armoring, where you put rocks or sandbags or something up to the beach. You can see there's a beach here where you hadn't really done that, and there's no beach here because it just erodes it away. The other thing you can do is you can constantly put new sand on the beach. So you can dredge it up from offshore, put it on the beach, or bring it in from other places, put it on the beach. And that's what they're doing in Waikiki to maintain the beach, because it's a huge monetary draw for the state of Hawaii. The other thing you can do is to ask people to build stilts on their house or move their house backward, something like that. And so that gives you more time to reside in that house before it's taken by the ocean. So, and this is a solution in part because you really, well, if sea level is going up, you really experience a problem with sea level when it's at its highest. So it's the highest tide, or when the wind is blowing just right and the moon is just right, so it makes the tide extra high. So it's the very highest time that you have sea level is when you experience a problem. And so as sea level rise happens, maybe a really high sea level would happen just once a century, but then if you have sea level rise, that becomes, instead of once a century, it becomes once a year. And then it becomes kind of instead of a once a century problem, it's every year a problem. And you have to do something like build your house on stilts instead of just suffering the loss of it. Okay, this happened, in fact, twice already this year. There were major sea level events, major enough that the Weather Service here gave them a name. There was Diedrich in January and Elsa in February, earlier, a couple weeks ago. And this is a picture from Bergen due to happening in Elsa. And you can see the water level. It was the second highest water level ever recorded in Bergen. And you can see the water level is right up to the dock level. So what do you do about this? If it doesn't happen very often, you can do something like what they're doing in Stavanger, which is they have these, they call them sausages, and they're filled with seawater, and you can kind of just install them, and it makes a temporary blockade for the water. And that serves, if you don't have to do that every year, then that's a solution. Just bring them out when you need to. This is a problem that people are seeing is going to be increasingly important in the future. So people are coming up with all kinds of ideas. One idea that was recently in the news was to build a dam between Scotland and Norway, and another one down here. And it was proposed as sort of a crazy idea. This is so crazy, I can't believe we're even talking about it. But they estimated the cost of the dam would be 250 to 500 billion euros, which is a huge amount of money, but it's small in comparison to the GDPs of the countries, Britain, France, Netherlands, Denmark, that would be saved by the sea level inundation. This is as the sea level rise, 0, 5, 10, 15 meters. This is the number of people that would be flooded. And so if you save those people from flooding, then the economic benefit, maybe it could pay for the dam. And that was the argument. It seems like a huge infrastructure project, and it takes 51 billion tons of sand to build that. But that's equal to the amount of sand that's used in construction projects just in 1 year all around the globe. So it's not totally out of the realm of possibility, some of these big infrastructure possibilities. But an easier way would be, well, maybe not easier, but an alternative way is to prevent this sea level rise from happening at all with one of the IPCC scenarios that has a flatter sea level change curve, which means reducing emissions and things like that. I note that the first author of this is a professor of oceanography at Utrecht. And I'll just show you the alternative. This was kind of a backup poster for this talk. And this is a picture I took in the Netherlands. And you can see sea level. And they have a lot of infrastructure associated with dealing with sea level in the Netherlands. This is one place near where this conference I was going to was. You can see sea level is higher than the neighborhood around it. Okay. I will close by showing you this figure, which is really, I tried to summarize everything that I've talked about in the past hour. We have sea level change happening on historical timescales and ice age timescales. There's different geological processes that are important for each one of these. On the very millions to billions of years timescales, there's plate tectonic processes that are important. Sea level, I hope I've emphasized this, is a very interdisciplinary problem. And I tried to list all the different sub-disciplines of the geosciences and engineering and other things in a list here. And so you can, and I've touched on each one of these things at one point in the talk. The major conclusions to take home are that these two processes cause regional sea level change that can be different in different places. And a lot of it's due to land motion, gravity changes are driving that. And it's mostly associated with new water going into the oceans or changing the temperature of that water. So you do things to the water. Global sea level change happens on geologic time scales, and those processes, in fact, the water volume and the basin volume, and they can act, and it occurs on all time scales. Okay, so I'll close with that, and I'll close with another photo of sea level. Thanks.
Thank you very much, Clint, for your extremely interesting presentation on sea level rises or sea level changes.
Yeah.
It's already about after 1, so
okay.
I think we don't have time for questions, but
okay.
You can be here.
Yeah, I'll be here for a few minutes after, yeah.
And next GEO-Wednesday will be in Norwegian. It's about impact craters by Henning Dybvik in 3 weeks or so. So I'll send out information about that. So thank you everyone for attending, and welcome back in some few weeks.
Okay.
Thank you very much to Clint.
Yeah, thanks.